Number 27. A little ball moving at 5 meters per second strikes the stationary ball of the same mass. After the collision, the first ball moves at 4.33 meters per second at an angle of 3 degrees with respect to the original line of motion. Assuming an inelastic collision, ignoring friction and rotational motion, find the struck ball's velocity after the collision.
Okay, so how to solve this problem? What we do is we basically make a diagram of the before and after picture. So at first we have the ball colliding at 5 meters per second against the second ball, which is the same mass, which is the second ball, and it's also the same mass, but it's not moving at all. And then so afterwards, there's a collision that occurs, and this ball moves at 4.33 meters per second at 3 degrees per angle. And what we need to find is how much meters per second this ball moves at the other angle. So what we do is that basically use the conservation kinetic energy. So what happens is that since this is an elastic equation, we can use kinetic energy to solve for the velocity of what this ball is moving at. So first we just use the equation, and we know that since the initial velocity of the second ball is 0, so we get to mark that out and put that as 0. So what happens after that is since m1 equals m2, we can then take the mass out and cancel these two out. And eventually we get this equation, which is v1 initial squared equals v1 final squared plus v2 final squared. And by plugging into the equation, and by knowing what v1 initial is, 5 meters per second, v1 final is, which is 4.33 meters per second, as shown in the after equation and the before equation. We had to plug it in and solve that v2 final equals 2.5 meters per second. And normally I think that's what the textbook asks, only for this velocity, but I'm just going to do the what the angle of this thing is anyways. So here it is. There's actually two ways you can solve it, which is using either the x component or the y component. So what you do is that you find how much you find the angles, you find the momentum in each x component. But since so for example I use cosine here, so for the first, if we're solving the x component way, we solve the momentum in this way for both of them. So you got one over here, x component over here, and x component over here. So that adds up to that adds up to having m1 times v initial of 1 equals m1 times v1 final times cosine 30. Since there's angle cosine 30 there, we need to find momentum here, and also m2 times v2 final of cosine angle here, which we don't know. And looking at this angle is supposed to be negative, and we can't really find that the angle is negative in this equation. So so you basically just plug in all the formulas in. You can cross out mass 1 and mass 2 since they're equal each other, and you get 5 meters per second equals 4.33 meters per second times cosine 30 plus 2.5 meters per second times cosine theta. Plug in the equation, you get around 60 degrees. And if you solve for 60 degrees, but it's supposed to be negative since the angle over here is a negative. And for the y component way, we just solve it so that the momentum equals 0 in the y component, since the initial since before there was no such y component movement, so there has to be no y component movement afterwards, unless they're both equal. So then you got mass 1 times velocity final 1 times sine 30 plus mass 2 final velocity 2 final times sine theta. You basically get it out since mass 1 equals mass 2. And oops, one sec. And so since this can be crossed out, we just basically take one of them to the other side like that, and we get this, and get 4.33 meters per second times sine 30 equals negative 2.5 meters per second. Oh, and 2.5 meters per second comes from the previous solved equation, where V2F equals 2.5 meters per second, if you're wondering. And we solve for it, and then we get negative 60 degrees. And this one's more accurate with negative, since the y component can tell whether it's facing upwards or downwards. And so the resulting answer is 2.5 meters per second at negative 60 degrees. And that's how you solve number 27.